So here we are in Matlab, and I have the picture or vector loop diagram of the Tepee right there so that we can refer to it. So we had started this simulation code already. We did it in a previous video to show the actual animation. So click the link if you want to review that. What we're going to do here now is add in the velocity and acceleration. The first thing we need to do is define velocity and acceleration of the input. So just like we defined position, since we made position be linearly increasing value of theta 2, then we want, since position is a line, we want velocity to be constant and acceleration to be 0. That's the easiest way to make things work. So we'll put that in there. T2D equals 1, and it can be anything that you want, just whatever speed you want the TP to move at. We'll just say 1 there. And then that is velocity, and then we want acceleration, T2 double dot equals 0. So then next we need to calculate the velocities. We'll have to put this in a for loop. So the reason we need to put it into a for loop is because we need to find the Jacobian at every single angle that theta 2 went through. So not just at one spot, but at all of them. So we'll have to calculate it in every single spot. So for count equals 1 to n. Then we'll define Jacobian. So from our formulas, that is just going to be 1 negative R2 times sine, R3 times sine of theta 3, and we need to index here. So we put that counter in there because it will calculate for theta 3 at that particular position. And then we go dot, 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 so it knows it continues on the next line. 0 R3 times cosine theta 3 count. So that gives our Jacobian. Now we need the B for velocity so that we can calculate velocity, and the B for acceleration so we can calculate acceleration. Say BV equals the B matrix we had worked out the math for. So that is we index in here as well. And that semicolon means make it a column vector. The comma means make it a row vector. So we want this to be a column vector. And then we have to multiply each of these by the velocity of the input. So now with B and J, we can calculate the velocity. So we'll say our theta dot matrix is going to equal inverse of J times B. So that is one way to do it. There's another way. We could say J backslash B. Either way works. And now that it will calculate theta dot, we need to extract which part of theta dot is R1 dot and which part is theta 3 dot. So just a quick peek at our equations again. Then R1 dot is in the top, theta 3 dot is in the bottom. So R1 dot will be the first element, theta 3 dot will be the second element. And we index here too. R1 dot of count equals theta dot of 1, and theta 3 dot of count equals theta dot of 2, second element. So acceleration will be very similar. remember that the Jacobian does not change. So we just need the new B matrix for acceleration. So now we've got those equations to look at. And we'll say BA, let's do first element, BA of 1 will be the top part of that. Now notice here that we index for T3 dot because that one is changing. We just calculated that above on line 35. Now the bottom part. So that forms the BA matrix. And then we need to calculate theta double dot. We'll do this one the other way. So both ways work. And then we pull out the accelerations from that. So now this should calculate all the accelerations. So once we've calculated, we're going to want to look at those. So we'll make some plots. So we've got a static plot here for position. So we'll copy it and change some stuff to make it velocity. So we'll define velocity vector as R1 dot and theta 3 dot. Make a new figure, hold on so that it remembers the lines to plot. And then we'll plot theta 2 velocity. And this line width command just makes the line thicker. So our X label is going to be the input, theta 2, which would be radians. And then the Y label would be velocities. And then a way to get the fancy angles and dots is to use LaTeX. So in order to do that, we have two lines for the legend. We name it, and then we set the interpreter. So the name is the legend. If we have R1 and then the underscore means subscript, and then that one would be the subscript. The backslash before it makes it a Greek letter. So we have theta 3 and R1, but we need to put the dots. So for that, we do backslash DOT. We need to put it inside the dollar sign, backslash DOT. Like that, and then again before the theta, backslash DOT. Then our title would be joint velocities. And notice we have meters for R, which would become meters per second, and theta dot radians per second. Those are joint velocities. So now to get joint accelerations, we'll copy this, make another plot. Okay, so here for acceleration, So acceleration is R1 double dot and T3 double dot. And notice how I have that apostrophe at the end for velocity and there for acceleration. And that's because the velocities and accelerations had calculated as row vectors, and we want them to be column vectors for this. So the apostrophe is a transpose, which just flips between row and column. So we'll make a new figure. Hold on, and then we'll plot acceleration. So X label won't change, Y label will become acceleration. And then here, so to get the double dot, we put an extra D in there. And then we want meters per second squared and radians per second squared. Joint accelerations. So let's run that. Okay, so we see the joint accelerations, and theta 3 double dot did not accelerate. That's this red line here. And remember, we had set our theta 2 double dot as 0. And since theta 3 double dot is exactly opposite it, they should have opposite velocities and same 0 acceleration. So that being 0 makes sense. And then R1 double dot started out super fast, and then it slowed down until the TP was flat out. So that makes sense. Let's look at velocity. So velocity, there's this like weird little spike here, and that happens because we did a numerical calculation for velocity. So because the TP is at a singularity when it's exactly folded up and exactly flat, that's why we would get that weird little spike right there. And then joint positions, got these. So theta 3 is decreasing, and then R1 is also decreasing as theta 2 increases. So this actually makes sense because even though the TP was expanding, look, we have to look at the x-axis here. So theta 2 started at 90 and it went to 0. So really we need to start looking at the right side of the plot, and we see that R1 increases, theta 3 increases as we go, and as theta 2 goes from 90 to 0. So that makes sense.